Okay, this is the last video. We're on the home stretch. Fortunately, I think this is the most complicated part, but let's do this. So, that being said, if this explanation still feels really wonky to you, please look at it in your book. The book and the lecture slides definitely go together, but obviously it's like a different perspective of how to learn these things. Okay, so now we know about um, the energy that comes in. We know something about wavelengths and selective absorbers and how the atmosphere helps us to have a higher temperature. But what we're going to do now is we're going to look at this like we have a certain amount of energy coming in. Where does it go and what happens to it? We're going to use, absorption and scattering and albedo reflection, and we're going to plot it out like you would your checkbook. Like, I make this much money, I have this many bills, this is where my money goes. And so I end up with this. So we're going to do the same idea with we have this much energy coming in, and this is where it goes. And this is kind of why we end up at this balanced temperature that we're mostly keeping in check, other than the gradually changing climate. Okay, please watch this video. It's helpful to start that out, thinking about all that energy as a budget. The way that we look at this is we start with a nice round number of 100 units of incoming solar radiation. So we have 100 units of that radiation coming in. And we're going to look at what happens to those 100 units. So first, we have 30 of those units that are not absorbed. They're reflected away or scattered away in some way. And it breaks it down. 4% of 4 units of that is reflected by the surface, 20 by clouds, and 6 is scattered by the atmosphere. So we had 100 units. We now have 70 because 30 reflected away. Okay, 19 units are absorbed by the atmosphere and clouds. So remember, we said that mostly the atmosphere does not absorb the energy from the sun, but it does absorb a little bit. So 19 of those units, so 30 are away. 19 of the units do get absorbed by the atmosphere, which is mostly in the stratosphere and the thermosphere. But there we go. So we're left with 51 of those units that came into the atmosphere from the sun are absorbed at the surface. Okay, so only 51 units of that solar radiation make it down to the surface. Now we're going to take those 51 units and we're going to break those down about what happens at the surface and like emittance and absorption and radiation with the atmosphere. So 51 units in, they're right here. Now we're going to go through all of these things. Nearly half, so 23 units, go into evaporation at the surface, okay? So remember, evaporation is a cooling process and latent heat is being stored. So of the 51 units, we lose 23 to evaporation of water, and that's in, rivers, lakes, but it's also from plants, all that stuff, okay? We lose 7 units through conduction and convection, which is kind of shocking because that's mostly how we heat the atmosphere. But we lose 7 units to that, and 21 units radiated away through infrared radiation. So, of the 51 units at the surface, only 21 units radiate away, but you can see that you don't see 21 on our schematic here. What you see is infrared radiation as a negative for our budget is actually 117 units. That's like way more than 21 units. So remember what we said about if an object is emitting more energy than it's receiving, then it has a net cooling. But we know that our atmosphere basically, for the sake of this, stays at 59 degrees Fahrenheit. So it's in balance. We don't have a net cooling. With climate change, we have a net slight warming. But what's happening? What's happening? So the planet, remember, the Earth is a black body. It's constantly emitting energy away, constantly, even at night when the sun isn't radiating on it. So the solar energy only comes in during the daylight hours, but the Earth emits all the time. So that those extra units of lost energy are because the Earth is radiating all the time. So it's still radiating away energy. Um, but notice, of these units that get lost, okay, down here, you'll notice that only 6 of those units actually get all the way out to space and get totally lost in our system. Okay, first we looked at it as just the sun coming in, and now we're looking at both how the surface interacts with the atmosphere. So, of those 117 units, 6 get radiated away, but the atmosphere absorbs, with those selective absorbers, 111 units. Um, it's retained by that carbon dioxide, water vapor, um, and all our greenhouse gases and clouds, because clouds are a different type of, like, they're a phase of water. They have a certain absorption as well. So now we're going to look at the other side of it, like what's happening with those 111 units and the atmosphere. That's this side of the schematic. So over half of that radiation is radiated back down to the surface. Okay, so we have 96 units of that energy that's absorbed, because these numbers look a bit different. So the atmosphere has 160 units to lose, not 111, but that's because it also had absorption from the sun. It's confusing, I know. But the take home from this part is that the atmosphere re-emits, it's not reflecting, it's absorbing the radiation, it's absorbing the long wave radiation here, and then it's turning around and it's re-emitting it down towards the surface, down, because it's re-emitting everywhere. So the surface gains another 96 units of heat energy, right? We were in a deficit of 117. No, wasn't quite it. Anyways, we were in a big deficit, and now we have another heat source, because it's the atmosphere actually giving us back heat energy to heat the surface. Some of the energy that the atmosphere absorbs does get uh, emitted out to space. That's about negative 67 units. So the take home is that the Earth's surface, right? Because we know that our atmosphere is heated from the ground up, right? We need the surface to be warm to change the temperature of our air. But the Earth's surface receives almost 2 times the amount of energy from the atmosphere and than it does from the sun. So really, the atmosphere, we have the sun fueling the system. If we didn't have the sun adding this heat energy, we wouldn't be able to emit at these temperatures to start with. But once we get that energy in between the surface and the atmosphere, there's a lot done with it to keep our temperatures at what they are. Okay, so now we have an ICLA for you to do. This pie chart corresponds with this graphic. There's actually a little tricky thing in there. There's like one extra pie slice, one more pie slice than there are places, but I trust that you'll be able to figure it out. So you are going to identify, these sections are numbered, you're going to identify what percentages of the solar energy that's coming in and where does it go? Where does it go? Here we have scattering by the atmosphere, reflected by clouds, reflected by the Earth's surface, on and on, absorbed, emitted, absorbed. No, it's all absorbed, because it's where that first schematic, where the solar radiation is coming in and then what happens to it. So that is basically the Earth's energy balance. The numbers get very complicated, like they don't match up quite as well for me at the end, but know that even though the Earth only gets sun half of the day, because of our atmosphere, our temperature and our energy stays in balance basically all the time. Okay, last little thing. This plot, we have some plots that kind of look like this. On the x-axis, we have latitude. So here in the middle is the equator. Then we have the poles at the two ends. And this is on the y-axis is how much energy that location gets per year. So this white line is incoming energy from the sun. And this red line is outgoing energy by the Earth emitting. Okay, So we're like pausing all the energy budget stuff. We're just looking at what's coming in versus what's going out. So you can see that in the middle, the white line is much higher than the red line. So in the tropics, more energy is coming in than is going out. So it's warming, right? That's what it is. Then in the poles, it's the opposite. There's not as much solar radiation coming in and there's more going out. So that means that we have a net cooling. So at about 38 degrees north and south latitude, that's the only place where the amount of ingoing and outgoing radiation is balanced. That's why here and like in the most of the US, we have 4 distinct seasons. We are in the area where the atmosphere is actually trying to balance out and take this surplus, the surplus heat, and move it to where there's a deficit, and take this cold air and move it to where there's a surplus to balance everything out. That's one thing to remember. The atmosphere is trying to always get in balance. It won't happen because it's too chaotic and there are too many variables. I mean, we are only into chapter 2 and we've talked about a lot of them, right? But that's its goal. Its goal is to try and balance this out. So part of the reason we get the crazy weather we do is because the atmosphere is trying to balance out this energy imbalance to make it all even. So it isn't only the atmosphere that does this. Actually, ocean currents also do it as well, but we are mostly going to focus on the atmosphere and how that does that. That is it. That is chapter 2. I hope you guys enjoy the snow. I will see you all when I get back on Monday. If you have troubles, please message me. And then please don't freak out. I just don't want anybody, if they're having issues, to like get really anxious about it. We will deal with what we need to deal with when I get back. Okay? Take care, you guys. See you soon.